Okay, hi again, everyone. Uh, so in today's class, we're going to be finishing up um, this last section of our chapter 2. So before we get started, let me just do a little recap of what we started to discuss yesterday, and that was the idea of upper bounds, lower bounds, so upper and lower bounds of a set. And in particular, we are interested in a very special upper bound that we give the name the supremum, or the least upper bound. So for upper bound, I'll write UB for upper bound. And we're also interested in a very special type of lower bound, something called the infimum, or another name for it is the greatest of the lower bounds. So for lower bounds, I'll put LB for lower bounds. Okay, and the idea behind all of this, so we went through the definition of it yesterday, so I'll just recap the idea of what all of this thing is. So all of this is taking place in an ordered field that we're going to call F. So the example that you should have in your head for F, right? So the example to keep in your mind is the real numbers with the usual less than or equal that you grew up working with. Okay, but this definition, if you are asked for this definition, you need to give it with respect to an ordered field F. Okay, so the real numbers is the example that you need to keep in your head if you have to explain it. But if you are asked the definition, you need to give the definition from the notes, which has to do with any arbitrary ordered field. Okay. And oh, I should also say, feel free at any time to um, chime in because it's a small class. If there's something you don't understand or any question you want to ask, feel free. You could either type it in the chat, or if you want to, you could just unmute your mic and tell me. Okay. Yeah, so the situation is we are in an ordered field and we have some set S. So let's just say S is some subset of this ordered field. And the example I usually like to give is an interval, but again, the set S does not have to be an interval, right? So for example, you could have some of this set over here. So the blue represents the set S. Maybe some of the set is down here. Maybe some of the set is up here, right? So the set doesn't have to be an interval. The set could be anything. It could even be a bunch of finite points. Okay. So this thing here in blue is your set S. Right? And the idea of an upper bound for S, so upper bound means that you are looking for an element, or elements, I should say, because for upper bound, there are many of them. So you're looking for elements U, such that these elements, since it's an upper bound, upper means it's bigger than. So these elements are greater than or equal to every element in the set S. So bigger than or equal to X for all X belonging to the set. So if we go back to this picture over here, if I'm looking for elements that are greater than everything in S, it's easy to see that these elements should lie over here. Okay, because if I take any of these elements, they will be bigger than every single element in the set. Okay, it doesn't matter that the set has like a gap in between over here. Okay, the main point is it's bigger than everything in that particular set. So the upper bounds live up here, and there are many of them. Now, what about the lower bounds? So for a lower bound, I'll call it L. Lower means less than. You're looking for elements such that these elements, let's call them L, are less than or equal to every element in the set S. Okay, and from the diagram, the lower bound should live down here. Okay, because we could see from this diagram that all these elements to the left of the set are all smaller than every single element in that set. Okay, so the lower bounds live to the left and the upper bounds live up here to the right. Of course, in this case, if a set has at least one upper bound, so most of the time there are going to be many of these upper bounds. If a set S has just one of these, we say it is bounded above. If a set S has just one lower bound, if you could just find just one lower bound, we say S is bounded below. And in this particular example, notice that for this particular set S, it has upper bounds and it has lower bounds. So it is bounded above and below. So in this particular example, S is bounded above and below. So when a set is bounded both above and below, we simply say S is bounded or a bounded set. Okay, so above and below means you are bounded. All right, so that's the idea of upper bounds and lower bounds. And again, the main thing to remember is that there are many upper bounds, many lower bounds. Right, we'll look at an example after this. Now, among all these upper bounds, there might be, and I use the word might here because we'll see in a case that we may not have this happening all the time, but among these upper bounds, there might be a very special upper bound, the smallest of these. So collect all these upper bounds. Which one is the smallest or the least upper bound? That one we call the supremum. Okay, so the way that you should picture this is that you have some set S. So this is your set. It is bounded above, so it has upper bounds. And now you're going to shrink these upper bounds. What is the tightest upper bound you could find so that it's right up against the set? In such a way that if you were to make an upper bound smaller than this guy, you will fall inside of the set. Right? So in that case, we're looking for a very special element over here, well, for this picture, and that element will be the least of these upper bound, and we call this element the supremum of S. And in a similar way, we could do the same story, but with the lower bounds. So among all these lower bounds, what is the tightest lower bound you could get? What is the best lower bound? So for the lower bound, it's reversed. For the upper bounds, you are decreasing them. You're looking for the smallest. For the lower bounds, you are increasing them. You're looking for the largest of them. Okay, so I'm increasing my lower bounds. I'm increasing. I reach very close to the set S until I reach a point where if I try to make this lower bound any smaller, I'm going to fall inside of the set. So this lower bound over here is very special. It's given the name, the infimum of S. Okay, so the supremum and the infimum are just very special types of lower and upper bounds. Okay, so that's what we were looking at yesterday. Let me give two examples, then we move on. So let's consider the set A being the set, it's a half open interval, so open at 0, closed at 1. Okay, so now we are in the real numbers. Here is 0, and it's closed at 1. So of course, you all know what the closed square bracket means. It means include that point, and the open curved bracket means you do not include 0. Okay, so this thing here is our set A. Or if you want to, your set S, doesn't matter what you call it. So this set, the intervals are the easiest sets to work with, by the way. right? But it doesn't always have to be intervals. We'll see later on what other sets we may run into and how to handle them. But for intervals, we are looking basically at all elements, all real numbers in this case, between 0 and 1, inclusive of 1. So we are looking at all x values bigger than 0 or less than or equal to 1. Right? That's the set over here. So let's see if we could figure out whether or not the set A is bounded above, it's bounded below, and if it is, does it have an infimum and a supremum? So for the set A, let's first do an upper bound. So what are some possible upper bounds for A? An upper bound for A is just a number bigger than everything in the set. So the set ends at 1. So just pick any real number you want, bigger than 1. 2, that's fine. You could pick pi. Pi is up here, 3.1, right? Or you could pick any of these elements. So the upper bounds, since we are in the real numbers means you are either rational, irrational, integer, whole number, fraction, any of those. So you could pick any of those, right? So all of these are upper bounds. So upper bounds, for example, any number bigger than 1, so maybe 1.1, 3/2, pi, right? E, okay, any of those numbers will work. All right, what about the lower bounds? So what are some lower bounds for A? So notice again, A ends at 0. Okay, so if we want a lower bound for A, we just need to pick any number less than 0. Okay, so all the lower bounds live here. So pick any negative number. If you're less than 0, you are negative. So -1 will work, -100 will work, -√2 will work, minus, I don't know, 4/17, whatever, right? So all of those are lower bounds. Therefore, A is bounded, right? A is bounded above and below, okay? Because it has an upper bounds and it has lower bounds. Therefore, A is bounded. All right. So now that we know A is bounded, what are, or could we figure out the supremum for it? Is there, among all these upper bounds, what is the smallest I can make these upper bounds? So again, you need to start with the upper bounds and slowly start moving towards the set until you can't move anymore. Otherwise, you're going to fall inside of the set. So notice that if you keep decreasing these upper bounds, once you hit one, um, you cannot decrease that upper bound anymore. And 1 is an upper bound, by the way. I know you're seeing that the set x is less than or equal to 1, but remember the definition for an upper bound is, let me go back to it. You're looking for elements or numbers that are bigger than or equal to every element in that set. So yes, 1 is in the set, yes, but 1 is also an upper bound for this set, right? Because 1 is bigger than every element or equal to, every element in this set. So yes, 1 is an upper bound for this set. Not only that, 1 is the supremum of this set. So you could choose to write supremum and then put the set in bracket, or if you want to, you could write it like this. It all depends on you whether or not you want to use a bracket. That's up to you. Okay, so the supremum turns out to be 1. This is the smallest you can make these upper bounds. If you try to get an upper bound smaller than 1, it will not be an upper bound. You will fall inside of this set. Okay, and for the infimum, so for the infimum now, we are looking at the lower bounds. So the lower bounds are all the way here, -1, minus pi or something over here. Right, so start with the lower bound. and slowly start increasing them until you hit up the set. So we're working with the lower bounds. We are making them bigger and bigger, greater and greater until we hit 0. Now 0 is not in the set, but it doesn't matter whether or not the lower or the upper bounds are in the set. That doesn't matter. Okay, so 0 is not in the set. Yes, that's okay. But notice 0 is very special because 0 is less than everything in the set. So 0 is a lower bound. If I try to make a lower bound bigger than 0, I'm going to fall inside of this interval. So 0 is like the best lower bound you could get, the greatest lower bound you could get. So we say 0 is the infimum of A, right? So that's your supremum and that's the infimum. Of course, this here is just like how to figure it out using a picture. We're going to have to learn how to prove these things in a more rigorous way. Okay, so we'll see how to prove them in a more rigorous way in a bit. Okay. So lower bound, upper bound, supremum, infimum. Yeah. So before we continue on our discussion, let's just look at this one last set. This set, again, let me just call it A. This set will be the set of the set of rational numbers, so the set of fractions, such that when you square them, you are less than square root 2. Okay. Or if you want to rewrite this set, you can write it like this: the set of rational numbers such that they are less, they are less than root 2. When you square them, they are less than 2, not root 2. Okay, so we are looking for all rational numbers. And in this case, we are going to take the underlying ordered field. Remember, all of this setting is taking place in, where is all of this taking place? This is all taking place inside an ordered field, F. And from what we discussed previously, we have two examples right now of ordered fields: the real numbers and also the rational numbers with same less than or equal. Okay, so the real numbers is an ordered field, the rational numbers is an ordered field. So far, we were looking at the setting taking place in the real numbers. Now, let's say I want to look at the setting now taking place over the rational numbers. Okay, so here is 0. Okay, so I want to try to write what the set is. Here is 0. So I'm looking for all numbers such that when I square them, I get a number less than 2. In other words, I'm looking for all rational numbers between or so I have this written bad. It should be x between plus and minus root 2, right? So I'm looking for all rational numbers between these two values. Now, these two values, square root 2, of course, you know square root 2 is an irrational number, right? If you've never seen the proof of this, you can look it up after today's class. It's a very nice, clever proof that the Greeks did. And anyone could understand the proof that they did. It's a proof by contradiction to show that root 2 is an irrational number. So root 2 and minus root 2 are not in Q. So root 2 and minus root 2 do not belong to the rational numbers because they are irrational numbers. But we are looking for all of the fractions in between here. So all the fractions in between here. For example, 1/2, quarter, right? So all the fractions in between here. Maybe here is minus 1/2. Now, let's try to do the same thing. Is this set bounded above or below? So of course, this set is bounded above. Take any number bigger than square root 2. So if you want to, take 100. This is an upper bound. For a lower bound, again, take minus 100. That's fine. That's a lower bound. So this set A is bounded above and below. In fact, you have a lot of upper bounds. All these elements to the right are upper bounds. Now, if we try to find what is the smallest or the least of these upper bounds, so we're trying to find the supremum. So we're slowly moving towards the set. And like before, we are going to hit up root 2. If I try to make an upper bound for this set any smaller than square root of 2, whatever that number is, I'm going to fall inside of the set. Okay, so it appears that square root 2 is the supremum of this set. But remember, well, I didn't have it here, but I could write it in. This element U, the upper bounds and the lower bounds, must belong to the underlying field. Okay, they must belong to the underlying ordered field. So in this example, the underlying ordered field is the rational numbers. So I'm only allowed to look at rational numbers. So yes, you want to say that the supremum of this set A is equal to square root 2. But you cannot do that because square root 2, look, square root 2 is not a rational number. And again, if we want to now look at the same thing, but for the infimum, so I'm looking at all the lower bounds, so everything to the left of the set, and I'm increasing. I'm making the lower bounds big and big and bigger, right? So I'm increasing them, and I want to find what is the greatest lower bound or the infimum. And again, I'm going to hit up this number minus square root 2. And if I try to make if I try to make a lower bound, well, first of all, I should say that these numbers, minus root 2 and root 2, so this one is not a lower bound for A. And this one is not an upper bound for A. Because in order to be a lower bound and an upper bound, right, you need to belong to the underlying field. And the underlying field we are looking at is the set of rational numbers. So minus root 2 and root 2 are not bound for this set, right? But we, of course, know what they are because we know about the real numbers. But let's pretend we didn't know about the real numbers. So if you try to make minus root 2 any smaller, or a lower bound any smaller than this guy, you're going to fall inside of the set. So again, what you want to write is that the infimum of this set A is equal to minus square root 2. But again, you cannot write that because minus root 2 and root 2 does not exist in this field. From the point of view of the rational numbers, these elements, root 2 and minus root 2, the rational numbers don't know about these elements. Okay, so in this particular case, so this is a subset of the rational numbers, A is bounded, right? It is bounded because it is bounded above and it is bounded below. But A does not have any supremum or infimum. Okay, so here's an example of a set that is bounded both above and below, but it does not have these elements. These elements do not exist within the field, so I cannot choose them. right? And what's the resolution of this? How could we solve this problem? How could I make it so that I do get a supremum and an infimum for this particular set A? Well, it's very easy. Instead of looking at the ordered field, the rational numbers, we know that the rational numbers live inside of the real numbers. So why don't I, instead of looking at this over the rational numbers, why don't I look at the same set over the real numbers? Then I could choose root 2 and I could choose minus root 2 because the real numbers know about these certain numbers. Okay, so the resolution for this, how we solve this problem when dealing with the rational numbers, that it's missing, it seems to be missing a lot of its points, is to use a bigger ordered field that does contain these points, and we'll see today that that field is the real numbers. That is what makes the real numbers so much more special, at least in terms of analysis, over the rational numbers. So that's the story so far. And what we want to do now is, because we will eventually need to prove, given a set, with practice, when I give you some set, you will just be able to look at that set and you will be able to figure out very easily what the supremum and what the infimum is with practice. But you will need to, in this course, prove that that thing really is the infimum and the supremum. So if we go back to this example, the interval 0, 1, yes, by this sort of argument with this picture that I drew, I'm telling you that the supremum is 1 and the infimum is 0. But this is not a proof, eh? This thing here is not a proof. So I need to write a proper proof of this thing in analysis. And now you're thinking, well, how are you going to write a proof for this? Because this thing is so obvious, right, from the picture. And can't you just always draw a picture of the set and be able to tell? And the answer is no, because I could come up with some really nasty looking sets where it's actually impossible to draw that, and it's very difficult to see what the supremum and the infimum of those sets might be. Okay, so there are some very even within the real numbers, there's a very difficult sets. So we will want to formalize all of this and prove it. Now, that means we're going to need some tool or some conditions that when these conditions are satisfied, it will tell me that that element is a supremum. And when these conditions are satisfied, it will tell me whether or not that element is an infimum. These are what are called characterization terms. Okay, so what we're going to start off today, right? So we went through all of this. Actually, we didn't go through this one. Okay, so we'll come back to this proof here, right? Because let's do the characterization term first, and then that will help understand exactly what is going on in this proof. So this is the same example we did. Oh, I just drew interval 0, 1, half open interval 0, 1. And this over here is how to formally prove that the supremum really is 1 and the infimum really is 0. This is the proof of it that I'm talking about. So the picture, yes, it's good to always be able to draw that picture and explain it to yourself and have that picture in your mind when you're writing this proof. But in an examination or when you're doing analysis, this is the proof that you need to reproduce, something that looks like this. Okay, not necessarily the same proof, because you will see there are many, many ways to prove these things. This is just one of the ways. So we'll come back to this proof, but what I want to do first is this, because those proofs are actually using these results. So it's looking a little bit scary, but I assure you, it's everything that I just explained, but it's just written mathematically now. Okay, so we'll do the characterization of supremum first, And what you should do at some point this week is sit and write down the proof for the characterization of infimum. So the supremum one is in the course notes. You have this proof. The proof for the infimum is the same thing, same proof, except you just change the inequality signs. Okay, but the proof idea is the same. Okay, so this is what we're going to prove. So let's go through it. The characterization of supremum. So this is how to prove something is the supremum of a set. So let F be an ordered field. And again, the example that you should have in your mind is the field of real numbers. But this works for any ordered field. The real numbers is just an example. So let F be an ordered field and A a non-empty subset of F. Then the following statements are equivalent. So the following statements are equivalent means both 1 and 2 mean the same thing. So 1 implies 2, 2 implies 1. Okay, so it's saying that an element U is the supremum of A, means or is equivalent to saying that U is an upper bound for A, right? So we know that the supremum of a set satisfies two conditions. First, you must be an upper bound because the supremum is a special type of upper bound. So first, the supremum is an upper bound. And what is this special condition? This special condition, another way of stating it, the supremum is the smallest of the upper bounds, the least upper bounds. So what's another way of saying that? Another way of saying that is for any small number, let's call it epsilon, any small positive number, there exists, or you could find an element in the set A, call him X, such that this element is bigger than U minus epsilon. So again, I know the first time you see this thing, it might look confusing, but let me draw the picture for you, right? You don't need to cram off that result. All you need to do is have this picture in your head, right? So this is some ordered field. So the set does not have to be an interval, but just for simplicity's sake, let's say that the set, what was the set, A or F? E. Let's just say for simplicity's sake, the set A is an interval, right? Just to make it easier for me to explain to you what that result is saying. It is saying, so this guy over here, this is the supremum. So U equal the supremum of A, right? And this is true, by the way, for any interval. And once you have just one interval, the supremum is the rightmost point, and the infimum is the leftmost point if you have an interval, right? You could prove that. Okay, all that thing is saying is that U is the supremum, means U is an upper bound for A. So from the diagram, that's easy to see. U is an upper bound for A because U is bigger than all other elements in A, right? All other elements in A are inside here. So U is bigger than all these elements. But the next condition had to do with some sort of epsilon, and you do U minus epsilon. What exactly is that doing? The second condition is saying, I'll write it here. This is the first condition. This is the second condition. It's saying that for any small positive number you give me, epsilon, there is, or you can find some element X belonging to the set A such that, and then there's some condition here. This is the condition students always forget. But I'm going to show you from the diagram. You don't even need to cram this off. You could see it from the diagram. So this is the supremum. What happens if you take a small positive number and you subtract that from U? So for example, what if U is equal to, I don't know, 5, right? And epsilon is 0.001. then U minus epsilon is 5 minus 0.001, right? So it's something a little bit less than 5. So the idea is if I take U and I subtract epsilon, I reduce U by a little bit, which side am I going to end up in? Am I going to end up on the left or am I going to end up on the right? I will end up on the left. Okay, so this point over here represents U minus epsilon. So this distance over here, okay, it's making an arrow for me, represents epsilon, right? So U minus epsilon is this point over here. So once you take the supremum and you reduce it, subtract a little bit from it, U minus epsilon, if U is the supremum, it will fall inside of the set. In other words, there's going to be an element. Okay, so what color do I use? Let's use this. There's going to be an element of the set X bigger than the supremum. Okay, you see that? So we took U, subtract a little bit of it, and we get U minus epsilon. And what happened? There's an element of the set A in between. So what is the inequality going to be? So for any, and this works for any positive number, any epsilon you choose, no matter how big or how small, the moment you subtract it, there's going to be an element of the set uh, uh, bigger than U minus epsilon. So for any positive number, there exists an element of the set A such that, and now we see what the condition should be, such that X, so look at the diagram, which is bigger, X or U minus epsilon. X is the bigger one. So such that X is bigger than U minus epsilon. This is the condition. Okay, and we figured it out from the diagram. That's all the characterization of supremum is saying. That the supremum is an upper bound for A. And if you take any small number away from the supremum, so if you work out U minus epsilon, you reduce the supremum by any little bit, you will find an element X belonging to the set A in between here. In other words, you will find an element X bigger than U minus epsilon, right? So let's see from the same picture if we could figure out the characterization of infimum. Okay, so this is characterization of supremum. What about the characterization of infimum? So it's the same logic we're going to apply. The characterization of infimum says that L is the infimum of a set if, first condition, L, so look at the characterization of supremum condition, and we are just going to adjust it for the characterization of infimum. So you don't need to learn, yes, it's good to learn both conditions, but if you know one, you could write the other one just by looking at the first one. So look at this part here. U is an upper bound for E. So if we are talking about the infimum, it will be L is a lower bound for E, right? We're just changing it, making minor adjustments. And the second condition is same thing. For any positive number, epsilon, there is an element X belonging to the set A such that, and now what are we going to write there? So we go back up to our picture. Where is the infimum? The infimum is over here, right? So this element here, L is the infimum. Infimum is over there. So what happens? So for the supremum, I took the supremum and I reduced it. I subtracted a small epsilon. For the infimum, if I want to fall inside of the set A, I need to add a small amount to it. Okay, so take the infimum, and we're going to add epsilon amount to it. So that's going to bring us over here. So this guy over here is is L. Write that better. It's the infimum, L plus epsilon, right? Increase it by a little bit. The characterization of infimum tells us that the moment you do this, no matter how small you increase L, there will appear an element X belonging to the set in between. Okay, so the mystery condition is, I just need to write what is the relationship between X and this number, L plus epsilon. So what is the relationship between this? Which one's bigger, which one is smaller? So it's clear that L plus epsilon is the bigger one, is bigger than X. Or if you want to, you could write it the other way. You could say X is the smaller of L plus epsilon, right? So you could write it this way, or if you want to, you could write it the next way. Anyway, it's fine. They both mean the same thing, right? So this here is the idea behind the characterization of supremum and infimum. It is capturing the idea that if you have the supremum or the infimum of a set and you try to adjust it just a little bit. So if you have the supremum and you try to adjust it, you try to reduce it by any small amount, there will appear an element of the set over here. In other words, actually another way of looking at this is that this element you get, u minus epsilon, is not an upper bound. Why is it not an upper bound? Because look, there's an element x bigger than it. So u minus epsilon is not an upper bound. So if you take the supremum and you try to reduce it by any small amount, what you end up with is not an upper bound. You don't get an upper bound anymore. And for the infimum, same thing. If you take the infimum, which is the greatest, the largest of the lower bounds, and you try to increase it by any small amount, so increase it by epsilon, L plus epsilon, what will end up happening is that this new number you get, L plus epsilon, is no longer a lower bound. It's no longer a lower bound because look, there's an element x less than the lower bound, or less than it, which means that this thing is not a lower bound anymore. Okay, so these are things you have to sit and think about this stuff for a while, or maybe seeing the proof will help. So what we're going to do is we're going to try to prove this one, the characterization of supremum. Okay, and you will have to sit and write down the proof for the next one, the characterization of the infimum, sometime this week. Okay, so it's an if and only if statement. It's an equivalent statement. So it means I need to prove one implies condition two, and I also need to prove condition two implies condition one. Okay, so this is what it means by the statements are equivalent. In order to do the proof, it's an if and only if. You need to prove one implies two, and you need to prove two implies one. Okay, so the proof of this is in your notes, by the way. So I'll follow along with that, but you could find different sort of proofs for this, but I'll follow along the one in the notes. So we're going to prove for this one implies two. So what is one? One is oh, never mind. Sorry, I wrote it poorly. These two conditions should be one. Characterization of supremum says that maybe it should read this. Condition 1 and 2, these should be one condition. Let me write it like this. Sorry about that. This should be one. This should be one. At least we're following the notes, right? So this is condition 2. Both of them together is a condition. And condition 1 is U equal the supremum of A. And over here, the condition 1 is L equal the infimum of A. And this entire thing together forms the second condition. Okay, so both of them together was the condition. Okay, so I want to prove 1 implies 2. So 1 is U is the supremum. I'm going to assume this is true. And I want to show this, and I want to show this. Okay, so suppose U is the supremum, right? That's what I'm assuming to be true. Suppose U is the supremum of A. What are the things I want to show? I want to show U is an upper bound for A. Well, that is true. What is the definition of the supremum? If you go back to the definition of supremum, it will read that an upper bound, U is the supremum if, so first of all, in order to even be the supremum, you need to be an upper bound. Okay, so suppose U is the supremum, then by definition of the supremum, I should say a supremum because we haven't proved that the supremum is unique, but it is. Then by definition of the supremum, U is also an upper bound for A, right? Because the supremum is a special type of upper bound. So I have the first well, I keep saying the first. I have the first condition of part 2 completed. So the next one is where we have to do a little bit of work. So in order to prove the next one, I need to then say for any or if or let epsilon be bigger than 0, right? I need to show that I could find an element in the set that satisfies this condition. Okay, so let epsilon be bigger than 0. Then notice that if I take U minus epsilon, this number is clearly smaller than U, right? Take any number, subtract something from it, that's the smaller number. Okay, in other words, since U is the supremum, in other words, U minus epsilon is not an upper bound. It's not an upper bound for A. Why is U minus epsilon not an upper bound for A? Because U minus epsilon is smaller than U. U is the smallest upper bound. U is the supremum, so you are the least or smallest upper bound. So U minus epsilon is smaller than U. So this guy is the smallest of the upper bounds. So U minus epsilon cannot be an upper bound then. Otherwise, that would have been the supremum. Right? So U minus epsilon is not an upper bound for A. If it is not an upper bound for A, then there exists an element belonging to the set A that must be bigger than it, right? Such that X is bigger than U minus epsilon, right? And that's what we want to prove. That's what we want to prove. Okay, because if you are not the upper bound of a set, if you are not the upper bound of a set, then there's an element in that set which is bigger than you. Right? That's all that all we have to do is just write it out. So that proves 1 implies 2. Okay, so now we need to prove 2 implies 1. So now I'm going to assume this condition and this condition as true. Actually, give me 1 minute. Okay, just give me 1 minute. Okay, sorry about that. All right, so where were we? Yeah, okay, yeah. So we're going to prove this condition and this condition implies U is the supremum. Okay, so how to prove that? So um, I'm going to say that, okay, we can write about. So suppose uh, condition 2 holds, right? So again, this is condition 2. Use an upper bound, and for any epsilon, there's an element in A such that x is bigger than u minus epsilon. So suppose that is true. Okay, so this part here is a proof by contradiction. So what do I want to prove? Required to prove u equal the supremum of A. If it's a proof by contradiction for this part, I'm going to assume the negation of that. What is the negation of u equal to supremum of A? I'm going to assume u, this particular element, is not the supremum of A. Okay, assume it is not the supremum of A. Okay, if you are not the supremum of A, there exists another upper bound, call him u prime. So let me write it like this. Then there exists another upper bound u prime of A such that, so u is not the supremum, means there's an upper bound smaller than it, right? The supremum is the smallest of the upper bound. So if u is not the smallest, there's another upper bound, u prime, smaller than u. Okay. All right, so this one here just have a little trick that you need to remember, and that is, if I tell you, so just aside, if I tell you, let's say if I tell you 2 is less than 2.5, right? If I tell you 2 is less than 2.5, then it's easy to see that 2 is equal to 2.5 minus some amount, right? That makes sense. Of course, the epsilon is a half. So all I'm saying is that if one number is less than another number, I could convert the less than sign into an equality in this way. I say, okay, I know 2 is smaller than this number, 2.5. So 2 is equal to 2.5 minus some little amount, or some amount, epsilon. That's the same idea I'm going to apply here. U prime is smaller than u, which means that u prime is equal to u minus some amount, right? How much amount? I don't know, because I don't know what is u, I don't know what is u prime. So I call that amount epsilon, right? Where epsilon is positive. So minus some small positive amount, and I go, well, it may not be small, but minus some amount, epsilon, and it will bring u down to u prime, right? So now I'm going to apply what, because remember, I assume condition 2 holds. So I'm going to apply this part here. This part is saying, remember, I assume this is true. So I'm going to apply this. This says that for any epsilon, I could find an element in A, which is bigger than this number, u minus epsilon. Okay, so look, I have an epsilon. So this is the epsilon I'm working with. Actually, in the notes, they use epsilon prime, right? So let's do that. So we'll use epsilon prime to denote it's a specific epsilon that we have there, where epsilon prime is bigger than 0. Then for this epsilon prime, which is bigger than 0, by assumption of 2, remember we said 2 is true, there exists an element, let's call them x prime, belonging to A, such that that element x prime is bigger than u minus epsilon prime, right? I'm just applying this result here. So for any epsilon, I'm using this specific epsilon prime, and this is telling me I could find an element x. So for this element, I'm calling him x prime, such that x prime is bigger than u minus epsilon prime. Okay? That's what I have here. But what is u minus epsilon prime? That is equal to u prime. Okay, so this means x prime is bigger than u prime. But u prime was what? U prime was an upper bound of A, and x prime belongs to A. So how am I getting an element of A bigger than an upper bound? Right, which is a contradiction. Right, it's a contradiction because this one is an upper bound and this one is an element of A. The inequality sign here is wrong. It should be the less than or equal, not greater than. Okay, so that's the contradiction. Therefore, what I assume to begin with is false. What did I assume? I assume U is not the supremum. So therefore, U must be the supremum. Okay, so that's the way the proof goes. So you see, no need to cram off the proof or anything. Once you write it down a few times and talk to yourself as you go through the proof, explain to yourself why are you doing each step, what is the aim, where are you trying to get to, what are you applying. And for this one, what was the trick I said? Yeah, the only trick you need to remember is once you have this line here, you need to say, okay, then u prime is equal to u minus epsilon prime, right? And from there, just apply the assumption of 2. Okay, so that is the proof of characterization of supremum. And you need to sit and write down the similar proof for the characterization of infimum. It's the same, but the less than changes to greater than, the greater than changes to less than. Okay. All right, so now that we have the characterization terms, we could go back to this example and we could see exactly how they are proving these things. So in this example, we are given a set A equal this half open interval 0, 1, which is in the real numbers. how are we proving that the supremum of this set is 1 and the infimum is 0? Of course, just by looking at the set, remember I told you once you have an interval, so an interval is alone, the supremum is the rightmost point and the infimum will be the leftmost point. You need to prove that. Okay, so let's see how the proof goes. So note first that x, which is an element of A, is between 0 and 1, inclusive of 1, right? That's what this set means. It means you belong to, you are a number between 0 and 1, including 1. So this means that 0 is a lower bound for A and 1 is an upper bound, obviously. So there are many ways to prove these sort of things, and it actually depends a lot on what the set is. Okay, if the set is an interval, you could use this trick we're going to do. If the set is not an interval, you need to be very careful about using this trick. Okay, so what's the trick? We're going to assume that 1 is not the supremum. Okay, so if you are not the supremum, so what you're seeing here is exactly the same idea behind how we prove the characterization of supremum. Remember, if you are not the supremum, what does that mean? This is how we prove what we just did. We assume what we wanted to show was not the supremum. That means that there exists another upper bound, call him alpha, such that alpha must be less than the supremum. Oh, sorry, not the supremum. I want to show it's the supremum. So alpha must be less than 1. And of course, both alpha and 1 are upper bounds. So x should be less than or equal to all of these, right? For all x in A, because x is the element of A, alpha is our upper bound. So alpha should be bigger than or equal to x, but strictly less than 1. Now what we're going to do is, in order to get a contradiction, I'm going to generate an element that is bigger than alpha. Alpha is our upper bound, so I should not be able to find any element of A bigger than alpha, but I'm going to do that. I'm going to generate an element of A bigger than alpha. So what's the idea here? You just take the average, right? You just take the average of these two. Actually, let me draw that. We have this, okay, yeah, so we have it here. Okay, let me draw a new picture. That picture kind of cluttered. Okay, so here's R. A is 0, 1, 0, 1, right? So what they are just saying there is that so 1 is over here and alpha is strictly less than 1, right? So alpha is over here, right? So I'm going to generate an element in between. So an element in between here is what? Alpha plus 1 divided by 2. That's the average, right? If I give you two numbers, A and B, how are you going to get an element in between them? Here's A, here's B. You could get an element directly in between them if you do A plus B over 2, the average, right? So just take the average of these two elements and you get a guy in between. Notice that this new element that I have generated, alpha plus 1 over 2, belongs to the interval, right? It is less than 1 and it is bigger than 0. Therefore, this element belongs to A. So what did I do? I have generated an element belonging to A, which is bigger than an upper bound. That should not be possible. Okay, so that's the idea of this proof. So now 1 plus alpha or alpha plus 1 over 2 belongs to A, and you see it is between alpha and 1. It's just the average of these two numbers. Okay, therefore this element here belongs to the set and is bigger than the upper bound. So alpha cannot be an upper bound, but we assume alpha was an upper bound. So that's the contradiction. Okay, therefore, what I assume to begin with is false. 1 is the supremum. And so, like I said, this only works really if you have intervals, because the whole reason why this number, when you take the average of two numbers, why that number belongs to the set is because the set is an interval, right? If the set were, you could imagine discrete points, individual points, then when you take the average, you might not hit one of those points. Okay, there's no guarantee you might hit one of those points. You'll see examples of it in the practice questions that I'll put up. Right, so this one only really works if it's an interval. So we've proven the supremum is 1. What about the infimum, which is 0? Same idea, same trick. So we're going to assume that 0 is not the infimum. The infimum is the greatest lower bound, the greatest of them. Okay, if you are not the infimum, then you can find another lower bound, call him beta, such that beta is bigger than 0, or 0 is less than beta, because we assume 0 is not the greatest lower bound. So there's another lower bound, beta, in front of 0, bigger than 0. And of course, because 0 and beta are both lower bounds, they must be less than or equal to everything in A. And again, we do the same trick. Take the average. What is the average of 0 and beta? So 0 plus beta over 2, right? Of course, you don't need to write the 0, but that's the number you see here. So now beta over 2 belongs to A because A is an interval. And beta over 2 is strictly between 0 and beta. So this is an element belonging to the set, which happens to be smaller than a lower bound. Okay, so beta is not, oh, so here is here's a typo, right? It should read, beta is not a lower bound. I think, yeah, I think in the course notes, it's correct, right? So the typo is just here. So beta is not a lower bound for A, right? And this is a contradiction, so that means that the infimum is equal to 0. So these are, well, this is an example of one way you could prove this for an interval, right? Of course, for different questions, it will depend. Okay, so moving on, we have some other properties of supremum. So this one, I will leave for you to read through, okay, because I did characterization of supremum. So this one, you can read through. It's using the characterization of supremum, but I'll just explain basically what this is, right? So again, the proof looks complicated, but each line in it, they're just using one or two ideas. All right, so this one is saying, if A and B are non-empty subsets of R that are bounded above with supremum, so A has a supremum, call it supremum A, and B has a supremum, call it supremum B. If I form a new set S, this set S is A plus B, where A is an element of A and B is an element of B. In other words, what are you doing? You are taking every element in A and adding it to every other element in B. So if you have two sets, take an element of A, add it with B. Take an next element of A, add it to something in B, and do all possible combinations of that. That is what this set S is, right? So this result is saying that this new set you get S is bounded above and has a supremum equal to the supremum of A plus the supremum of B. Okay, another way, oh, I shouldn't say another way, that result is often written like this. that the supremum, if A and B are sets, that result is usually written like this, that the supremum of A plus B, now A plus B is a set. That's the set they are calling S, which is the set of points A plus B, where A comes from A and B comes from B. Okay, so this is usually how it's written. The supremum of A plus B equal the supremum of A plus the supremum of B. Okay. In the notes, they just, instead of saying A plus B, they put S. Right, but the idea is the same. Okay, so I'll leave you all to read through this proof. We could talk about it next class if you like. Another proof from that is so let F be an ordered field if you have two subsets of F, two non-empty subsets A and B, such that X is less than or equal to Y whenever X is in A and Y is in B. If the supremum of A and the infimum of B exist, because they may not exist, we saw that, then the supremum of A is less than or equal to the infimum of B. Right? So what is the picture with that? So that seems like a lot, but again, once you draw the picture, it's not too bad. So this is your ordered field F. All that is saying is that you have two sets. Okay. Let's say this is one of them. This is your set A. You have another set up here. Call this guy B. Right? All that is saying you have two sets A and B, which is a subset of F, and every element in A is less than or equal to every element in B. So take an element in A, call it X. Take an element in B, call him Y. So we are saying X is less than or equal to Y. Right? Every element in A, where I tell you where these things come from. X is in A and Y is in B. So every element in A is less than or equal to every other element in B. What this result is saying is that the supremum of A, which lives here, right, is less than or equal to the infimum of B, which lives here. And now that I drew the picture, you see, well, you see an idea of why this should be true. Okay, but you have to sit and try to prove this. So the supremum of A is less than or equal to the infimum of B. Right? So proof left as an exercise. Again, try these proofs because I put up these solutions to all of this. So before looking at those solutions, try the proof and see if you can figure it out. So you have some examples on that. I'll leave that for you to go through. Yeah, so yeah, so now we're getting into the last few slides. The idea of the completeness axioms. I should say axioms, the completeness axiom. So before we do that, notice, so let me go back up to these examples. Yeah, it's a good example. So this example we just looked at, where we proved, given the set A, which is half open interval, 0, 1, remember we proved that 1 is the supremum and 0 is the infimum. But notice in the set, 0 does not belong to A, right? 0 does not belong to A, but 1 does belong to A. So what I'm trying to get at is, if a set has a supremum or an infimum, that supremum and infimum may or may not belong to the set. Okay, the supremum and infimum may or may not belong to the set. In this case, this was the infimum, and it does not belong to the set. And in this case, the supremum of A was 1, and indeed it does. I say it does, I write it doesn't. Equal to 1, it does belong to A. Okay. If it happens that the supremum of a set belongs to that set, it's also in the set, we give the supremum a fancy name. Well, not a fancy name, but we give it a name. We call this the maximum of the set. And we write max A. Okay. If the infimum belongs to the set, so in this case, the infimum does not belong to the set, so we can't use it for this set. But if the infimum belongs to the set, we will call that infimum the minimum. Do I have any other examples? Not really. Okay, we just look at the definition. All right, so the definition is saying let F be an ordered field, and we have some subset. If alpha, which is the supremum of the set A, is also in A. So once you figure out what the supremum is, and once you prove that it's the supremum, just check, is that number in the set? If the number is in the set, then we call that the maximum. And we write, instead of the supremum of A, you could write the max of A. Okay, so the max simply means you are the supremum and you belong to the set. What about the infimum? So if beta is the infimum of A and you also belong to the set, then beta is called the minimum of A, and we write it as beta equal minimum of A. Now, what happens if you have, in this example, we had the infimum was equal to 0, but 0 is not in A, right? So in this case, the maximum of A is equal to 1, since the supremum belongs to A. And in this case, the minimum of A, now the infimum is 0. 0 is not in the set. So we'll see that the minimum of A does not exist. The set has an infimum, yes, but no minimum. Okay, because 0 is nothing. Right, so that's just two new definitions for you. So whenever they say something is the max or the min of a set, this is what they mean. They really mean the supremum and the infimum, but it belongs to the set. Okay. All right, so this last definition is what is essentially what this whole chapter was based on. So the table I usually draw is we started out with sets and we had the natural numbers, the integers, the rationals, the reals, and the complex. And then we went on to fields. And okay, so we went on the fields and then we had ordered fields. Right, so for fields, this is a field, this is a field, this is a field. For ordered fields, we lose the complex numbers, right? Remember the reason why? So we lose the complex numbers because, I'll put here again, since C has I, which is not equal to 0, but the square of it, which is -1, is less than 0. If you are an ordered field, the square of any element should be positive, right? That's the reason why complex numbers is not an ordered field. The last property is what? So we have a tie so far between the rationals and the real numbers. So what makes the real numbers beat the rational numbers is this thing that we call order complete. Okay, order complete. An order complete has to do with when are you guaranteed to find the supremum and the infimum? Okay, so it's this definition. An ordered field F is said to be order complete if every non-empty subset of F that is bounded above or bounded below has a least upper bound, so that's supremum, or greatest lower bound, which is infimum, in F. So the crucial thing is that the supremum and the infimum needs to be in the field. Okay. So this property has a lot of other names, and you need to be familiar with all these names. Okay. So if F is complete, we also say that F has the least upper bound property, or LUB property, or completeness property. Sometimes this is called the completeness axiom. So all these mean the same thing in this definition. So what is it saying? It's saying that an ordered field is ordered complete if every non-empty subset that is bounded above has a supremum, and if every non-empty subset that is bounded below has an infimum. In other words, if you live in an order complete field, and you tell me you have a set that is bounded above, I know it has a supremum. The supremum exists. If you tell me you have a set that is bounded below, I know the infimum exists, right? So if we go back to this example where we had the rational numbers, right? This example with the rational numbers, and we looked at this set, the set of all rational numbers such that the square of it is less than 2, right? This set was bounded above, bounded below, but it did not have any supremum, and it does not have any infimum. So look, here is an ordered field, Q. Here's an ordered field where there are bounded sets with no supremum and infimum. That is why we cannot use the rational numbers to do analysis, because we want the guarantee. In analysis, we want a guarantee. The moment I have a bounded set, I have a supremum and an infimum. We need that guarantee in order to do analysis. Okay, so that is the definition from the point of view of any arbitrary ordered field. But we are interested in one in particular, the real numbers. Okay, so this example is that example that I just showed you. The set of rational numbers such that the square is less than 2. This does not have a supremum in Q, right? The supremum has to belong to the field. So the rational numbers, if I ask you, is the rational numbers order complete? You will tell me no, it is not order complete, and you could give me, if you want, this example or many, many other examples. But if you want to, you could give me this example and you could say, here is a set in the rational numbers that is bounded above but does not have a supremum. So I put here, the obvious supremum is square root 2, but that does not belong to the ordered field. So among these fields or these sets that you have encountered, which one has this nice property? So that is given by this result, this theorem. There exists a unique ordered field R with the least upper bound property or the completeness property, such that it contains the rational numbers. So in some sense, this is, well, okay, so there's a couple ways that you could construct the real numbers, right? The way that this theorem is referring to, so I put here the proof is omitted. You can have a look at the proof if you want. I don't recommend it. It's a very intricate and complicated proof. but it's at the end of this book, The Principle of Mathematical Analysis by Walter Rudin, right? And it uses the idea of something called a Dedekind cut. Yeah, so in some sense, this is how, well, not in some sense, this is exactly how the real numbers are made. Okay, so what do I mean by all of that? For all of those sets there, if you think about it, if you start with the natural numbers, right? 1, 2, 3, 4, and so on. If I ask you to use that, could you see how they got the integers from the natural numbers? The integers, they just negated all of these guys. They added 0, and then they put back the same natural numbers. Okay? So these are the natural numbers. In some sense, these are the negative of the natural numbers, and then they just add in 0. So in order to construct the integers from the natural numbers is a very straightforward way. You essentially, what you're doing is you are adding to it the additive inverses, right? And how to go from Z to Q? Well, I now have all of the additive inverses, but I don't have the multiplicative inverses. For example, 4. What is the multiplicative inverse of 4? It's a quarter, but a quarter is not an integer, right? So if you take all of the, it's a bit more complicated than this. It's called, you need to construct something called the fraction field. But the basic idea is you take all of the integers and you invert them. And then you multiply all possible combinations together, right? And you get things that look like this, P over Q, where P and Q are integers. And of course, you know, Q, the denominator, is not 0. So to go from the integers to the fractions is again kind of straightforward if you to think about at least. You just take all of the integers and you flip them. You invert all of them to form fractions. How do you go from Q to R? The next step up. So this one, well, let me write what R is. So R is Q, the rationals, together with the irrationals. So in order to go from Q, the rationals, to the real numbers, I need to add to the set this thing. I need to take my rational numbers and I need to add all the irrational numbers to it. The problem is, how do I define an irrational number? You see, for a rational number, it's very easy to define. These are what it looks like, P over Q, right? That's what all rational numbers look like. What is the definition of, okay, let me rephrase that. How would you write down a general irrational number? So the definition of an irrational number is not so clear. It's not so clear how to define these things, and that is what this thing, the Dedekind cuts was doing. So in order to go from the rational to form the real numbers, to construct the real numbers, what you had to do was construct and add to it all the irrational numbers, right? And in doing that, what you are essentially doing is a process that allows the real numbers to have this order completeness. It allows the real numbers to have this LUB, or least upper bound property, right? So if you want to know, oh, I said, well, yeah, if you want to know how it's done, you could have a look at this thing. I do not recommend this, but if you're curious, you can have a look at it. You're of course not going to be tested on that. That's well beyond this course. What was I going to say? Yeah, so if someone, you know, on the street asks you, why does the real numbers have the least upper bound or the completeness property, you could tell them it has that property because it was made to have that property. That is how it was built. It was built to have that property. Okay. It's sort of like they ask you why, or So like why do airplanes fly? Because they were built to fly, right? That is the way they fly because they were constructed to do just that. So why does the real numbers have this property? Because it was constructed to have this property, right? So that is a little thing on this stuff. Uh yeah, so we just have so three more or three more slides or one more thing that we need to discuss. But I want to go through. So the last thing is, so I'll just introduce it now, but we'll cover it in our next class this week. So the next result or the last thing in this section is the Archimedean property in R. And very easy, all this says is that, you know the natural numbers, the set of natural numbers, it's unbounded above in R. It has no upper bound, right? So that is saying, you see the set, the natural numbers, so it has a lower bound, right? It starts at 1. So any negative number, 0 is a lower bound. What about the upper bounds? It has no upper bounds, right? It's kind of obvious when you look at it. But how do you prove that? It turns out in order to prove this, you need this completeness property of R. So this completeness property, yes, it's a very technical condition, but it's needed in order to prove very simple, obvious things. If I ask you, how would you prove that the natural numbers has no upper bound, right? You need this property to actually prove that. Something very simple, but you need that property. And there are some consequences of it, which I'll go through with you on next class. We could prove maybe one or two of them, right? That's used a lot in analysis, and then we'll talk about what it means for a set to be dense in another set. So we finish up these last three slides in our next class. Okay, are there any questions you have for me?